Hey everyone, welcome back, and today let's solve Leetcode problem 2401 titled Longest Nice Subarray. So we're given an array nums consisting only of positive integers, and we call a subarray of nums to be nice if the bitwise and of every pair in that subarray of all the elements that are in different positions or indices in the subarray, their bitwise and of each pair has to be equal to 0. And we want to return the length of the longest nice subarray in the input array nums. And it kind of defines subarray real quick to just be a contiguous portion or part of an array. Right? And note that subarrays of length 1 are always considered to be nice because they really only have one element, so the end is going to be assumed to be 0. So in example 1, we have our input array nums to be 1, 3, 8, 48, and 10. And in this case, the reason why we have an output of 3 is because that is the length of the longest nice subarray that we can find. And in this case, it would be these three elements, 3, 8, and 48. Why is that? Well, because in this subarray of these three elements, 3, 8, and 48, we see that we have all the pairs that are in different positions would be this 3 and this 8, this 3 and this 48, and this 8 and this 48. And the bitwise and of all of those pairs elements, like 3 and 48, 3 and 8, and 8 and 48, they all have a bitwise and value of 0. And there is no longer nice subarray with more elements that would still continue that all pairs having a bitwise and of 0 property. And so 3 is the maximum length that we can get. In example 2, we have our input array nums to be 3, 1, 5, 11, 13. And in this case, we only have an output of 1 is because each element itself is considered to be nice, but we can't have any more elements added together in the subarray to still have that property because none of the elements do actually have a bitwise and of 0, at least not consecutively, to make a subarray, and so our output is 1. So for the constraints here, we see that the length of our input array nums is going to be within 1 and 10 to the 5th power, and any value in the input array nums is going to be within 1 and 10 to the 9th power. So pretty large inputs, at least relatively, kind of telling us that, okay, we can't really have worse than a linear time solution, nothing like n log n or anything like that. Either we can have a logarithmic time complexity or a linear time complexity, right? Which brings us to the main observations that we can really make in the context of this problem. And one very key observation, or takeaway if you will, that we really need to make from the problem statement and examples is that for any subarray to actually be nice, all the elements have to have disjoint bit representations. And I'm also going to comment that out because that's how we know that all the bitwise and of all the unique elements is always going to have a bitwise, or rather disjoint, sorry, looks like I don't know how to spell today, bit representation. And this is applying for all of the elements because we're going to check all of the different elements that are at least in unique pairs. Let me just kind of respell representation. I hope that's right. It looks to be spelled correctly. At least I hope it is, right? And what does that really mean in the context of this problem? Well, if we're actually processing the array and we're adding numbers to our current subarray that we're building, the moment we actually find a number that breaks that condition, meaning its AND result with the current subarray is non-zero, we know we have to immediately remove the elements from the left until we restore that condition, until we get back to a valid subarray where the current element that we're trying to add still has a bitwise AND of 0 for all elements. So while it doesn't have a bitwise AND of 0 for all elements, we have to keep shifting our pointer to the right and removing elements from the left to actually get or restore that condition and get a valid subarray again. Right? So to actually efficiently track which bits are actually in use, like I was just kind of talking about, first we're going to have, of course, a variable used bits. That's actually going to store the OR of all the elements in the current window. And again, the pointer technique. This is essentially a sliding window algorithm. It is still a two-pointer method, left and right pointers, and the left and right pointers are going to be used to expand and shrink the window for new elements and changing elements as we actually iterate through the input array. Right? And so this is going to also, the sliding window is also going to make sure that we don't have too slow of a time complexity, keeping it worst case linear and keeping it, as efficient to solve for this problem without exceeding the input constraints. So let's go ahead and get into the code here. So let's actually first initialize all those integer variables like I just talked about. We'll get use bits. We'll get left. In fact, I'll do this on separate lines. I think it's a little bit easier. They're all going to be initialized to 0 because that's kind of where we start and build off from in our input array nums. So the used bits, the reason why it's first initialized to 0, that's actually going to keep track of all the bits that we're currently using in our subarray using that OR operation. And of course, we start off with 0 used bits because we haven't actually built any subarrays yet, because we haven't started iterating through the input array yet. Now this left is going to be our left pointer. Right, this is going to represent the start of our sliding window that we gradually increase to the right as we don't fulfill the condition while we add new elements of having a bitwise AND of 0 for all unique pair of elements in the current subarray. And the max length is simply going to store the maximum length of any nice subarray that we found so far as we've iterated through the input array nums. And of course, I'm going to initialize that to be 0 as well. So now let's actually begin iterating over the array with the standard for loop here. So for every right is basically going to be our right pointer, and it's going to be our iterator that we iterate through each element exactly once with in the whole input as well. So for right in the range of the length of our input array nums, a very standard for loop iteration here. Right, simply expanding the window by adding numbers or elements one by one. That we're trying to add to our current nice or potentially nice subarray. Now, when we're adding this current element nums at right, does it break the condition? Meaning, do we have any elements that this nums at right value doesn't have a bitwise AND of 0 with? Meaning it has a non-zero bitwise AND operation with any of the elements, the current value that we're adding nums at index right. So if that's true, or rather while that's true, we have to actually restore that condition by removing the leftmost elements and increasing or incrementing our leftmost pointer to account for that offset, or rather to account for that condition. So the way we'll check that is we'll have a while loop and actually have a parentheses after the while keyword here. While used bits is non-null or non-zero, and I'm trying to find that on my keyboard, there it is, while that AND operation at nums at right, while it's not equal to 0, because of course we want it to be 0, so while this condition is breaking, we want to actually break or decrease the length of our current nice subarray by removing the leftmost elements and incrementing our leftmost pointer in the integer left, right? And again, what we're really checking in this while loop here is effectively, while use bits is non-null, meaning we have actually still some bits in our current subarray, it's not 0, and the nums at right is not 0 with the current element. Basically, we're checking if we add nums at right, does it introduce any overlapping bits where the bitwise AND of any pairs with the current element doesn't equal 0. And if it is true, meaning we do actually enter this while loop here, we have to actually or rather, nums at right does actually share common bits with elements in the window, regardless of where they are or what they are. And so we have to actually shrink the window to remove those overlapping elements and shrink the window to get a valid nice subarray again. Because, of course, we want to have a bitwise AND of 0, meaning we have 0 common bits with any of the elements. And so if we don't get a bitwise AND with nums at right for any of the elements in our current nice subarray to be 0, we know it has some common bits with some elements, and so we have to remove them until we don't have them anymore, and until we have a valid subarray. So while this is true, while we don't have a valid subarray, we can actually shrink the window from the left and increment the left pointer accordingly to do this. So first we'll increment or update our left bits. This is again the number of bits that we have in our current subarray. This is going to be like a set of used bits. So we have to actually simulate removing the leftmost bit from the current subarray. And the way we're going to do that is going to use this operator, right? It's going to be the or rather XOR operator, and we're going to remove nums at left, and then increment the left pointer by 1, kind of simulating that we've removed this current leftmost pointer and moved 1 to the right, shrinking our window by 1 in this current iteration of the while loop here. And the reason why this works, again, use bits XORed by nums at left. That's going to remove nums at left again from the set of used bits, and it's going to work, again, XOR, this kind of caret symbol that you see here, it's going to reverse the effect of an OR operation, right? Getting us or simulating removing that element by inversing or kind of reversing the effect of what we did when we actually added it to the current nice subarray. And then to actually shrink the window by moving the leftmost pointer 1, we have to actually increment the left pointer until our condition is actually restored. So we're going to keep doing this while we still have overlapping elements. Now, once this is not the case, once we actually do get a valid window, now let's actually update our used bits to have this current right pointer or right element, nums at right, and maximize the length for this current iteration for this current valid subarray that we just got. So first, let's update used bits. And again, the order really doesn't matter, I wouldn't say in this case. We'll update the used bits by nums at right, basically adding nums at right, the actual element to the number of set of used bits that we have for the current nice subarray, because now it's actually valid. Now we can actually add it in without having any overlapping elements, which we handled the logic for in this while loop here. So once we actually do that, now let's actually get the maximum length. What if the maximum length is smaller than what we've seen in this current nice subarray. What if the current nice subarray is larger than the maximum length that we found so far? Then we have to actually increment it and update the maximum length accordingly. So it's going to be the max of max length itself, in case this is still the larger value, or the length of our current window, which we know we can compute by the difference between our 2 pointers, right minus left, plus 1. The reason why we do plus 1 is to actually account for that index of 0 or 0 indexed offset to actually get the accurate length of the current window. We're adding nums at right to the set of used bits in the used bits integer, and we're actually updating the maximum length that we found so far with this current potential longest nice subarray that we just made valid in this current while loop iteration. And we're going to do this for every right value or nums at right value that we try to add as a new element to our nice subarray. And effectively, once we process all the elements in this for loop here, once it's actually done executing, once it terminates, we want to return the maximum length. And this maximum length would actually contain the longest or max length nice subarray that we found in the entirety of the input array nums, based with amongst all of the valid nice subarrays in the input. So unless I made any syntax 0, 0, there should be accepted and there should be a valid solution. Okay, let's see what I did wrong here. Invalid syntax. Sorry, looks like I forgot in. And the in keyword is very important, guys. Sorry about that. But now, as you guys can see, this really is just about as efficient as you can get it to be. So on a high-level rundown, how does this solution actually work as a whole? Effectively, once we actually initialize the number of used bits we have, or the set of used bits we have for the current subarray is what this is tracking, and our 2 pointers and the maximum length, then we have to actually start iterating through the input array nums using that right pointer and expanding our window. And if we actually if we actually want to add the current element nums at right, if it actually does violate the nice subarray condition of having no overlapping elements, we have to actually remove elements from the left until it is actually restored by removing the leftmost element and incrementing or stimulating that by incrementing our leftmost pointer 1 forward in each iteration while that's still not met. And we have to also track our active bits, again using that used bits set of bits, and use the XOR and the AND operator to actually efficiently add and remove the numbers. Here we were actually removing nums at left, and here we were adding left using the XOR and caret operators, right? And so for the actual final result, the reason why we're returning the maximum length is because that would actually store the maximum length that we've seen amongst all of the valid nice subarrays that we build as valid nice subarrays in the input array nums once we actually finish processing the array. So for the runtime complexity of this solution, like we talked about briefly before in the high-level rundown, it is actually linear just to keep it as efficient as possible. It is a big O of n solution. Why? Because this really is just on a high-level rundown, a one-pass solution with one singular iteration or for loop here. Each element that is actually added to the window once and removed at most once if it breaks the logic of a nice subarray, and that would be an amortized big O of 1 operation per element, or a constant big O of 1 operation per element. And so really overall it's a big O of n, or linear time total time complexity. And for the memory or space complexity, believe it or not, this is actually a constant big O of 1 space complexity. Why? Because we're not actually using any extra data structures or any auxiliary memory. We're actually using only a few integer variables like used bits, left, and max length, all of which are simply just integers. They do not grow with the input size linearly, and so the memory or space complexity is constant, meaning it's big O of 1. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.